Hello everyone and welcome. My name is Annibale Panichella and today with Cynthia Lim, we're going to give a critical reflection on mutation testing practices for machine learning. Mutation testing is a very popular testing process which can be traced back to the 80s, and its overall idea is to assess the quality of the test suite. The starting point is that we have a class production code and the corresponding test suite that exercise the production code as much as we want. And mutation testing usually relies on a mutator generator to create program variants, each of which contains a small artificial fault or syntactic change. So we assess the quality of the test suite by running the test suite against the class under test in isolation and then to inspecting the result of the execution. A good test suite should pass on the original program but should fail on the artificial mutant, and we would say in jargon that the mutant is killed. And our goal as serial killer for faults is to try to kill all the mutants. This is the overall process for traditional software, but with rise of popularity of machine learning, researchers in the latest year have also tried to define mutation operator for machine learning application. A very nice overview of the existing research can be found in this paper published at ICST 2020, where the author classified more than 20 different operators that also apply at different layers and levels in the machine learning pipeline. For example, some operators aim to alter the input data in the training set. Other operators aim to change the architecture decision about the model to train, for example, parameter values and even the type of model itself. Other type of operators work at model once has been trained, so on the actual complete model, by changing the number of layers or making some path infeasible and so on. So what we want to discuss today is just thinking about what are we really testing or what are really mutating when we do mutation testing for machine learning.
To reflect on mutation testing for machine learning, I first want to speak a little bit about the commonly used paradigm in software engineering, the test-driven development or TDD paradigm. Here, when one wants to write a program, one first starts with writing different tests that will be important to that program. As soon as the test suite is established, only then you start writing your production code. And you start with a little bit of it, you run that against your test suite. If the test doesn't pass, then you go back and you improve your code. And as soon as the tests pass, you can go on and gradually build up your program. Now, this TDD paradigm is a bit like how we train machine learning models in supervised machine learning. We have input data, output labels, and we want for systems to associate the input with the given output. For example, if we have different pictures of animals, we might have those pictures, but also the associated labels, and we want for our automated models, based on the pictures, to give the right animal label. To do that, we also go through an iterative procedure. The practitioner specifies a model that initially in its default form probably will perform very poorly on our training data. That's why we have to gradually improve it. We do that through optimization procedures as coded in machine learning frameworks. And as we do that, we optimize in such a way that we get closer and closer to actually predicting the right input to output relations as given by our training data. So as we do that, at some point, hopefully, we are able, for a given input in our training data, to predict the right output. Actually, we might not want that to be 100% matched. Then we might think the model overfitted. So typically we have a bit of a softer criterion than in actual testing in TDD. But if a certain percentage of our test cases pass, of our images and our labels, then we're happy and we consider the model to be converged. However, even then, we could say our images for training, the training data, that those were our test suite. We could say that the model that was iteratively improved was the code under test. But if we look more closely, there even are more test suites involved and more programs and maybe even more programmers. As for the test suite, as soon as our model converges in training, we tend to also run it again against unseen test data that has similar characteristics to the data that we trained on, but it hasn't actually been seen. And we would expect for the performance of our model to then still be equivalent to the performance that we had at training. So if it turns out that the converged model performs really poorly on our test data, the model is not right, and we have to go back to the drawing board. We have to retrain and refine, or even maybe choose another model to use. Then as for programs, of course I only now spoke about models, but before that, the practitioner has typically scripted some instructions that initiated that model. And as the training was going on, optimization frameworks were used that typically are encoded in machine learning frameworks. So there are actually different programs involved and different test suites used, even though the training and evaluation of machine learning can be likened to testing and test-driven development. With that, we need to rethink what the mutants actually are in this setup. In current mutation testing for machine learning works, we've seen mutations being proposed, operators being proposed for data and for model specifications before training and post-training to the trained model. Now, these source-level pre-training operators that are on data actually, in this type of paradigm, would not really be production code. Rather, they are test cases. Rather, we might amplify test cases by modifying the data. So that would not be mutants in a mutation testing setup. As for the model, those changes could be considered to be valid production code mutations, but still then we have to think of their realism. In terms of the specification the human practitioner does, indeed, there could be different ways to configure. We might mutate in different ways. At the same time, as a model has been trained, if we want to evaluate it or if we want to then later do something else with it, we typically do not iteratively improve that with small changes to an already trained model. We would not typically delete some connections in the middle of a neural network as soon as we trained. Rather, if we want to change the model, we retrain the whole thing. So these are differences between the machine learning practice and the software engineering practice for normal programs that we probably should be more aware of.
Aside these technical aspects, there are also some philosophical questions that we need to answer and that are related to the hypothesis underneath mutation testing. The first hypothesis is the competent programmer, with the idea that the competent programmer makes a small mistake. But this doesn't match 100% the machine learning world, because we have both a real programmer but also some optimization routine. And the final product comes from the joint work of both. The developer may decide which architecture to choose, which are the parameter tuning, and write the glue code to run the optimization routine. But then the final product is created by the optimization routine itself, which is also written by human developers. So can we talk about, in this case, about competent programmer? Can we say that the machine learning model is competent? We can argue that's not the case. So this hypothesis definitely needs to be revised according to this new paradigm, machine learning programming, and the different stages that compose the machine learning pipeline. The second hypothesis in mutation testing regards the coupling effect. The idea is that if a test suite can detect small syntactic changes, which is also, we call them mutants, we'll be also able to detect larger bugs, hopefully real-world bugs, that are somehow coupled to the small ones. And this is the overall idea behind mutation testing. What we argue, however, that this hypothesis may not hold again for machine learning, because we have two actually scenarios. The first one is that a tiny change in the configuration setting can lead to a completely different machine learning model. So the syntactic change can be small, but the final product can be completely different, and then violating the concept of coupling effect. We can also have the other way around case, where we have two completely different models, also with completely different architecture and generated by different optimization routines, for example, deep learning and a simple logistic regression. But for certain problem and data set, the two can be exactly equivalent. So in this case, even though there are large changes, in the end, the two programs are the same thing. So this also poses challenges again, whether the coupling effect makes sense and how questioning mostly what can we consider as a small change in the machine learning world. And this is also a call for arms for our community to have a better and more empirical study on this hypothesis, but focusing on machine learning. That being said, I will thank you, all of you, for listening to us, and we hope to see you during the conference. Ciao!
Yes, Good, competent, competent.
56 people.
Yeah.
Yeah, good audience.
I think this is a huge group. People love it. So they're all.
Yeah. So now.
Hello, everyone. We are live, and thank you so much for this great work. I mean, it's a near paper, and it's really supposed to challenge our thinking, and you really have done so. We love it, right? So we have a lot of nice comments around mutants. So my first question to you is really, so when you talk about black box testing, don't you mean high order mutants like semantic, more intelligent mutants? Because I agree, as an industry, we're really trying to do use cases. So could you sort of expand a bit on if you thought about that sort of fault injection mutants, more complex mutants?
Yes, so let's say that there was actually one of the main points we started with since discussing about this topic is because we thought that some of the mutants are very simplistic. At least if you look at the model level, if you, for example, just change a tiny neurons, or for example, just the connection between them, is very simple. In the end, for machine learning, what we want is that the model extract patterns, for example, from images. So maybe what we need to test are the patterns. Does the model learns the right patterns, rather than dropping off one of the neurons or dropping one of the transition? And indeed, we think that the semantic, so higher level order mutation, but based on semantic, is definitely important in this case.
Yeah. Okay, so there is also a question here. What would be a realistic mutation operation? How would it look like for you?
Yeah, I think here that we need to generally think of. I mean, there is the concept of changing your input output, I think, and mutating data, which still is mutation, but maybe not the mutation testing framing, depending on what you see the data to be. And we've been arguing, we feel it's more of a test case input-output assertion than the code itself. But it depends also a bit philosophically where you are, because if you do consider it to be a good representation of the phenomenon and part of your model, then it might actually be part of your product. So this is something I think we need to articulate better. From the more traditional mutation operation orientation, I think that what we argued, the glue code maybe that the programmer writes, that would most traditionally fit. Although again, what you generate out of it, it's actually different artifacts. So I think that having changes there on realistic faults people make when writing that definitely fits in a traditional study. But it maybe is just a tiny part of the whole view that we would have.
Yeah. So isn't your point a small change really could lead to a completely different model, true also for traditional software? So, for example, reverting a Boolean condition can change the behavior of the method completely.
Yes, that's true. That can change the behavior, but does not change the structure of the code. So if I just revert, you still have the two branches of these conditions. By machine learning, if I change the parameter setting, I can have a completely different model. We can go from 3 layers to 20 layers or 50 layers, or I can even completely change the model. So if you have a classical simple linear problem, and I choose to use deep learning, the model I get is mostly equivalent to just a linear regression model. But the two models are completely different. One is a simple equation, and one is extremely complicated, and they are in practice identical. So here the concept of equivalence or what makes different is a bit more blurry. You can have a tiny changes in the parameter setting leading to a completely different model in terms of structures, not only about behavior, but you can also have two models that are completely different in terms of structures, but exactly behavioral identical. And I was making the example of the linear model of the deep learning model.
So I think that here the metaphor indeed is what we're searching for. So what exactly corresponds to what is also the instruction we give to train a linear model or a non-linear model. Is it like a specification we give to a team, which is our machine learning library, to make it? And as such, are we then generating different programs effectively? Or is this, again, part of a holistic single thing? So is also a different model